Hello guys, welcome back to Mezon African Motives. Still working on engineering science N3, that is working on heat. So in this part, we are going to be focusing on question number 5 of August 2017. So the first part on 5.1, we are given in this part, that is give the meaning of the coefficient of area expansion. Take note, we are working with area expansion of a solid and name the unit in which it is expressed. All right, so this is what we are given in this part. All right, so the coefficient of area can be given as the change in area per unit area, that is the change in area per unit area per degree change in temperature of the solid. All right, then the unit is per degree Celsius. All right, so whatever that you're going to have, it's per degree Celsius. That is the unit that we are going to have. All right, so that is what we're given in the first part of our question. Then we have got question 5.2, where we are given a condition whereby water is being heated. So we are given that is the second part of our question. Let us check the information that we have. Water is heated from 20 degrees Celsius. So we're given the initial temperature, that is 20 degrees Celsius to 90 degrees Celsius. All right, so we've got T1, which is 20 degrees Celsius, to the second temperature of 90 degrees Celsius in 1 hour. So we are given the time frame that is of 1 hour, in this case by 30 kg of a fuel. So we are given the mass of the fuel in this case, which is given as 30 kgs with a heat value of, so this is the heat value of the fuel, which is 31 megajoules per kg. Take the specific heat capacity of water as, so take we are given the specific heat capacity of water, which is given as 4,187, that is kilojoules per kg degrees Celsius. All right, and assume no heat is lost. So take note, no heat is lost in this case. All right, so this is the information that you're given. And on 5.21, we are given to calculate the change in temperature. All right, so we have, as we can see, that the water was being heated from a temperature of T1, which is 20 degrees Celsius, to T2. So this is going to give us the change in temperature in this case. All right, so the change in temperature given as T2 minus T1. So that is our final temperature of 90 degrees Celsius minus the initial temperature of 20 degrees Celsius. So that is going to give us 70 degrees Celsius. That is the change in temperature in this case. All right, then we move on to another part of our question, which is on 5.22, where we are given to calculate the heat value delivered by the fuel. Take note, the heat value delivered per hour. So it's very, very important, because we are given a condition that this is taken, the mass was delivered or the change was occurred in 1 hour. So meaning to say, we are not going to change anything, because this information is given per unit 1 hour. So our 5.22, we need to calculate the energy in this case, which is given as from our formula sheet, that is the mass times the heat value in this case. So we have got the mass of the fuel, which is that, take note, this is the heat for the fuel. So you're going to use the mass of the fuel. So E is going to be equal to the mass of the fuel, which is 30 kgs, times the heat value of that fuel, that is given as 31. Take note, this is megajoules per kg. So this is going to give us the energy in joules, which is going to be 930. Take note, this was measured in mega joules per kg. So meaning to say, our answer is going to be in mega joules like this. All right, so this is the energy that was, or the heat energy that was delivered by the fuel. Then on 5.23, we need to calculate the volume of water heated in cubic meters. Take note, we need the volume in cubic meters in this case. All right, so how can we calculate this volume? Given in this case, all right, so we need the volume in this case. Let us consider what we can obtain. we have got the heat in this case that we actually calculated, which we know that in this case, we can refer, okay, let us refer this way since we need the volume 5.23. So we need the volume, but this volume is supposed to be expressed in cubic meters. And with this information, there's nothing that has got volume direct from our formulas. But if we consider the mass of water in this case, let's say we consider the mass of water, then from the mass of water, we can express it as a volume in cubic meters, since we have a relationship that we can convert from the mass in kgs, where we know that 1,000 kgs is equal to 1,000 liters, which is equal to 1 cubic meter. So as we are going to work with the kgs, then we convert the kgs to cubic meters. So that is the easiest way that we can do. All right. So where can we obtain this mass of water? From the energy that we have. If this is the energy that is used to heat water, therefore, we can refer this energy as equal to the heat that is affecting our water in this case. So we are going to say that, or let me just write down here. So we are going to say the energy that is used by the fuel to heat the water is going to be equal to the heat that is for the water in this case. So this is Q for water, which we know that the Q for water, which is the energy for water, is simply the mass times the specific heat capacity of water times the change in temperature. Remember, it was the water had to change its temperature from the initial. So this specific heat capacity, we are referring to the specific heat capacity of water. All right, so this is what you're going to have in this case, of which we've got our E in this case in megajoules. So we can calculate mass from there, the mass of water. Like I said, we need the mass of water so that we can convert to cubic meters. All right, so what can we do to obtain the mass? We can simply divide by the specific heat capacity of water times the change in temperature, the specific heat capacity of water times the change in temperature in this case. All right, so this is going to, we are going to remain with the mass in this case. So meaning to say the mass is going to be equal to the energy, everything over the specific heat capacity of water times the change in temperature. All right, so we have everything in this case. We have got all these values. The energy from our fuel in this case, that was 930 megajoules. So that is 930 times 10 to the exponent of 6 to replace the megajoules in this case. The specific heat capacity of water, we are given our specific heat capacity of water from this information that is given as 4,187. Take note, this is kilojoules. So we are going to multiply by 10 to the exponent of 3 to convert this one to joules. So we multiply by 10 to the exponent of 3. So that is going to be 4,187 times 10 to the exponent of 3 times the change in temperature, of which we calculated this change in temperature before. Our change in temperature was 70 degrees Celsius in this case. So we are going to use this in degrees Celsius since our specific heat capacity is given in kilojoules per kg degrees Celsius. So that is why we are supposed to use the change in temperature in degrees Celsius. All right, so we're going to use as it is as a 70 in this case. The change in temperature was 70 degrees Celsius. All right, so this is going to give us the mass. Like I said, this mass is measured in kilograms, that is in kgs. So we are going to obtain something like 3,173,086, which is our mass in kgs. But if we are to consider, we need the volume in this case in cubic meters. And I said from this relationship, 1,000 kgs is equivalent to 1 cubic meter. So that means we can obtain our volume from this part. All right, so let's consider this to say 1 cubic meter or 1,000 kgs. So here I'm going to write as cubic meters. All right, so we've got 1,000 kgs is equal to 1 cubic meter. So if 1,000 gives us 1 cubic meter, what about 3,000 173,086 kgs. How many cubic meters are we going to have? So this is going to be more. So we're going to divide this one by 1,000. That is going to give us the volume in this case. So therefore, our volume is going to be, if we divide 3,173.086 by 1,000, we multiply by 1 cubic meter. Our answer is going to be in cubic meters. So that is going to give us something like 3,173 to 3 SF, to 3 decimal places in this case. So that is what you're going to have in cubic meters. So we are now having the volume in cubic meters as per the instruction that we are given. So this is how you play around with your formulas and also with the information that you're given. How can you change a certain unit to another unit? That is the conversion of units is very, very important in our syllabus. All right, so that is our question 5.23. Then we check 5.3. We are given to calculate the increase in area of a copper plate with the dimensions 3 meters by 2,5. So this is a rectangular format that we are given. So we are given this as a rectangular format that is measuring 3 meters by 2,5 meters in this case. All right. So the question is to calculate the increase in area, meaning to say we are talking about the change in area in this case, all right, of a copper plate with dimensions. All right, these are the dimensions. It is heated from this temperature to this temperature. So meaning we've got T1, which is 10 degrees Celsius, to this temperature, which is our second temperature, which is 240 degrees Celsius. So how can we calculate the change in area? All right, so we know that from our formula, we can calculate the change in area as, all right, so let me write it this way. Okay, so in this case, if we are to check, we actually need the linear coefficient of expansion for copper in this case. So we need the linear coefficient of expansion of copper in this case, because we are dealing with a copper plate in this case. All right, this is a copper plate. So from our information sheet, what are we having in this case, or from our physical concept that we have? Let us check what are we having in this case. All right, so this is what we have. Okay, we need the linear coefficient of okay, this is the one that you are given in this case. All right, so this is the linear coefficient of expansion of copper, which is given as 17 times 10 to the exponent of -5. All right, this is supposed to be times 10 to the exponent of -6. This is actually a mistake that we are having here. All right, so let me check what we got from this part. All right, let me check what we got in this case. All right. All right, so this is actually the same. All right, so our coefficient, the linear coefficient of expansion of copper, that is 17 times 10 to the exponent of -5 per degree Celsius. All right, so this is what you are given. All right, so this is the one that you are going to apply in this case. All right, so we are going to use 17 times 10 to the exponent of a -5. All right, so let us see what you're going to have at the end. All right, so we have got 17 times 10 to the exponent of -5 in this case. All right, so this is per degree Celsius. All right, so meaning to say, from our formula, we are supposed to have, we are talking about the change in area in this case. So our change in area is going to be 2 times. So for us to have the area expansion is 2 times the linear coefficient. So it's 2 times alpha like this, meaning to say we have got the area expansion, all right, times the original area times the change in the temperature. All right, so this is what you're going to have, meaning to say our change in area is going to be 2 times our linear coefficient of expansion, that is 17 times 10 to the exponent of -5 times the original area. In this case, we multiply these two sides, which is 3 times 2,5. Remember, this is a rectangle. So the area of a rectangle is given as length times width. All right, so that is length times width in this case, or length times breadth. All right, then times the change in temperature. We saw that the formula is T2 minus T1. So meaning to say we are going to subtract our T2, which is 240, minus T1, which is 10. All right, so this is what, or this is how we are supposed to have our information. All right, so we can use our calculator to simplify everything. All right, so, okay, I'm having two calculators now. All right, so this is what I'm going to have on this side. We have got 2 times 17 times 10 to the exponent of -5 in this case, all right, times the change in area, times the original area, which is 3 times 2,5 multiplied to 240 minus, I'm going to open bracket here, 240 minus 10, like this. All right, so this is what you're going to have, which is going to give us something like 0, 0,58. Okay, that's 0, 0,5865. All right, so our change in area is going to be 0, 0,5865, which is measured in square meters in this case. All right, so this is how we're supposed to have this according to the information that we are given in this case. All right, so if you check here, according to our linear coefficient of expansion of copper in this case, that's times 10 to the exponent of -5. All right, so this is how you attempt these typical questions. All right, so let us check the other part of our question in this case, which is 5.4. All right, so in question 5.4, we are given that steam is generated in a boiler. So we are given conditions that in this case, steam is generated in a boiler at constant pressure. Determine the following for 1 kg of, so take note, this is for 1 kg of steam. So meaning to say everything is taken per kg. All right, 5.41, we are given to determine the saturation temperature of the liquid enthalpy, which is at 377 kilojoules per kg. Take note, we are talking about saturation temperature in this case. So this is an application where you are using the steam tables in this case. All right. So what you ask yourself is, what am I given? I'm talking about saturation temperature, which means you're talking about water in this case. So this is the enthalpy of liquid, which is HF. So we are given HF as 377 kilojoules per kg. So what you're going to do is from your steam tables, you're going back to your steam tables at 377 when HF is 377. All right, so let's see what you're going to have when HF is 377. All right, so we need at a condition where HF is 377. All right, so this here, all right, so 377. This is, all right, so this part, it's at 385. All right, so let me check here. We need all right, this part here, this is what I'm having. So if you check under HF, all right, so we go under HF on your from your steam tables. This is what you're going to do under HF. So you're relating to HF. So this is what we need. You need the saturation temperature, which is TS, which is measured in degrees Celsius. All right, so this is what you need in this case. All right, so we are going down. All right, so let us go down on under HF. Remember, this is HF, this, or that is 1, 2, 3, 4. That is the fourth column in this case. So if you check under the fourth column at the end, in this case, that's 1, 2, 3, 4. So this is for HF. So if you check, this is where we have got 377 under HF. And this is the column for temperature TS. So what is the corresponding temperature there? It is 70 degrees Celsius in this case. All right, so this is pressure. Sorry, this is pressure. It's because, okay, let me get back to this information here. All right, so sorry for that, guys. Sorry for that. Sorry for that. Let's check back. Temperature is on the second on the second one. Temperature is on the second part. All right, so the second one. All right, so we need the second part here. So this is what we need. This is our HF from the fourth part. Said 1, 2, 3, 4. So this is temperature on the second part. So it's 90,0 degrees Celsius. All right. So that is the temperature that corresponds. So this one, you simply take it from the information. So this is 90 degrees Celsius. All right. So that is what we are going to have in this case. If our HF is 377, our temperature is going to be 90 degrees Celsius. All right. So our saturation temperature TS, all right, so 5.41. So TS is going to be 90,0 degrees Celsius. All right, so it is the same thing on 5.42. We need the enthalpy of dry saturated steam. Dry saturated steam in this case, which means we are referring to HG, that is for dry saturated steam. If the temperature, the saturation temperature is 54 degrees Celsius, meaning we are given temperature this time. Our temperature, saturation temperature is 54 degrees Celsius. What is the corresponding value for Hg? That is the question. All right, so let us check from our steam tables. When our saturation temperature, remember temperature is on the second column. So this is where we have our temperature. Then let's check where we have got our Hg. All right, so if you check here, this is where you have got your Hg on the that is 1, 2, 3, 4, 5, 6 on the 60th part here. On the 60th part, that's where we've got our Hg measured in kilojoules per kg. So you go under the second column for tempos. You are given temperature this time to say your temperature is 54 degrees Celsius. So you go under the temperature, then straight to Hg. What is the corresponding value? All right, so this is what you're going to have. So let us go. We say the 60 column. So we are going under temperature. This is 54. All right, at this point. All right, so this is our temperature TS here at 54. So we are going straight to the 60 column, straight. All right, so this is 1, 2, 3, 4, 5, 6. So this is our Hg, the corresponding value for Hg, which is 2. So it's 2599. As we saw the units, it's kilojoules per kg. So this is the corresponding Hg when our temperature is 54 degrees Celsius. All right, so this is how you answer this type of a question. All right, so let's check another part. So another part, all right, so here we obtained Hg as that was 2599 kilojoules. All right, so this is kilojoules per kg. All right, then we need the pressure, the final part, the pressure of the boiler. If the saturation temperature is 357 degrees Celsius. All right, so we simply go to the pressure to the temperature in this case, then we refer to the pressure. What is the corresponding pressure at that point? All right, so let's get to our temperature, 357. All right, so we need 357 on our steam table. All right, temperature of 357. All right, so this is going to be, all right, here we have got up to 222. All right, 357. Let's check on top here. We need 357. Let's check on top. All right, 300 here. So we need, okay, let's check first what we are going to talk about. We are given temperature. We are given temperature and we want pressure. And if you check, your pressure here is measured in kilopascals. All right, so let's go to 357. So we are going to 357 on temperature. 357, that's here at this point, 357 degrees Celsius. And the corresponding pressure is at 18,000 in this case. All right, so meaning to say our pressure is at 18,000, and the units, we saw that this is measured in kilopascals. All right, so this is how you answer this type of a question. So in this case, we saw that our pressure is going to be 18,000. which is measured in kilopascals like this. All right, so this is how you answer, guys. These typical questions is just direct. Also, the STEAM table you are given in exam, whenever you are in exam and you're answering this question paper, check on your question paper, is there a requirement for a STEAM table? If there is a requirement, request for a STEAM table. That is for you to answer this type of a question. Do not enter exam without the STEAM table. All right, so that's it, guys, from Maison African Motives. Till we meet again.